if you want to conceptualize in water a solitary wave, think of this figure here. If you look on the side of this, you will see definitively a sesh type profile. No question about it. But that is it, one dimension from here to here. That's sort of one way to conceptualize it. So now I'm going to go into a more technical portion of this lecture. I'll talk about water wave equations and a different formulation. So the water wave equations here, the water wave equations are listed here in a domain where you have free surface, here's your domain, and a rigid bottom. The velocity potential, and Q is the velocity potential on the free surface. Okay? And eta is the free surface. So y is between minus h and eta, x1, x2 horizontal. You have to solve the Laplace's equation with derivative boundary condition 0 at the bottom and two conditions on an unknown surface. We call this the kinematic condition, eta t, phi y. Eta only a function of x. And phi satisfies, phi and eta satisfy this equation, which is the pressure condition of the moving equation. And I leave in surface tension. G is gravity. So these are the equations. They're hard for a lot of reasons, and they've been around since at least Stokes. They're hard because you have an unknown free surface, and the equation is nonlinear. So if you want to solve it, you have to find that free surface, then solve it. But free surface is part of the whole dynamics. So what I'm going to talk about for a bit today is a reformulation. I don't know today if I'll derive it, but I will in Eugene Sharpie's seminar, 1 minute club implementation. But there are two equations we find. We worked with Focas and Muslimani on this in 2006. Eta and phi, think of rapid decay in x. And we have two variables, eta and q. Remind you, q is the free surface velocity potential. So you have eta and q. An integral differential equation depending on k. K is a parameter. Think of it like Fourier variable. And another equation which is the velocity, is the pressure condition on the free surface. There is no free unknown surface in this. It's two equations, two unknowns. If you solve it, you then get eta and q. After you have eta and q, that means you know q here, and then you go back, you have a Dirichlet problem to solve for phi, knowing the top eta, knowing q at x and y equilibrium. So you know phi at the top, phi y is 0 at the bottom, and you solve the plus equation, so it's a fixed equation. So you've removed the depth. You've removed the free surface. I considered this interesting, and we worked very hard with Thanasis on this, and Muslimani. And so a lot of what I have to say is trying to convince you that you can work with this in a very simple way, extremely simple. And if I have time, I'll explain some generalizations. If you go to deep water, then Kosh, KH, goes to e to the KH. And sinh goes to e to the KH, so this equation simplifies. Well, the variables A and Q were introduced by Zakharov at least in 68, the earliest I know, in his Hamiltonian formulation. Craig and Sulam derived Dirichlet-Neumann series in terms of A and Q. And they prove that those series converge from the one-wave equations. We connect what I had to say earlier to these series. But this is a summing, if you will, of the series. Note A to t, if you go to the equation for the kinematic equation, I wrote grad phi dot grad angle on the left side, just bring it to the right side. This is nothing but the normal derivative, proportional to the normal. So A to y equals zeta, n, that is, the normal is this. So you just get nothing but this dot n, gradient phi dot n. So A to t, if you find A to t, you get the normal derivative. Hence you have a relationship between the normal derivative and the Dirichlet condition, which is phi equal to free surface. So here are some of the things we've done, and the next few minutes you can just relax, because I'm going to just go into that more, into these aspects in more detail. We find conserved quantities and new integral relations. We find the classic asymptotic reductions. 1 plus 1, quote de Vries, nonlinear Schroeder. Deep and shallow water. Any general formulation should contain both deep and shallow. In one, it does. We also find 2 plus 1 Benny-Luke equation, and from that, Kadamsev-Peffer-Schmidt. Now, the Benny-Luke equation I'll have more to say about, not only in this lecture, but in Beijing, because that was derived by Dave Benny in 1964. And for some reason, largely been ignored. But I think it shouldn't be. It's a very nice equation, and it's sort of the first approximation that have waves going in two directions. Somewhat easy to work with, it's just a scalar equation. For whatever reason, it wasn't studied much. And then with Terry Howe, a student of mine, just graduated, we derived non-local equations for waves, internal waves, 1 and 2 free interfaces. I'll talk about that a little bit later. Connected Dirichlet-Neumann operators, asymptotic reductions to intermediate long wave Benny-Luke, and once you have Benny-Luke, from that you can get KP and study KP type equations. Higher order asymptotic expansions of 1 and 2D subterranes. Dirichlet-Neumann map, well, it comes from the non-local equation. If you take the cosh and expand it for small a, and cinch expand it for small a, then take the Fourier transform, you get a series times a to t, and a series times this operator into q. After you take the inverse Fourier transform, k goes away, so you get the operator that was in front of this times the operator in front of that. That operator here is the Dirichlet-Neumann operator G. And this agrees with Craig and others. Linearize the system. Well, if you get rid of eta, just take the leading term. Eta is 0. This thing, that non-local equation goes to this integral here. Okay? Just get rid of eta. Kappa squared is k1 squared plus k2 squared. This is 2D. You use the Fourier transform, you get the Fourier transform of a to t and the Fourier transform of gradient q. If you go to the other equation, the pressure equation, this is what the first term looks like. Get a system, take two derivatives, qt, use this, you get the linear dispersion relation of waves. Well, now, you get integral relations. How do they come out? Take k to 0. This goes to 1. Cosh of 0 is 1. Cinch, these cancel. This goes to 0. You're just left with a to t. Integral of a to t is 0. That's conservation of mass. Go to the next order. You get a very nice relation. The derivative of the center of mass is proportional to momentum, which means the center of mass moves linearly in time. A known relationship, very hard, not so easy to get out of classical water waves. This comes immediately. And then you get all sorts of higher order variable identities. here's the first one. I haven't seen the latter ones, but for all I know, they're there. Certainly they're there, it's just whether people have used them or not. Well, one of the things you think about when you do water waves is asymptotics. Why do you think asymptotics? Well, water waves are a hard problem. Free surface. So applied mathematicians made huge contributions early on by reducing this very hard problem, free surface problem, to a fixed problem. And that's what I talk about by going into various approximations. So we do non-dimensionalization. The primes are non-dimensional variables, x1 over L. L is a characteristic length. Eta has characteristic amplitude. C naught is the square root of GH, typical velocity. So you go through non-dimensionalization, you get three small variables. A over H, small amplitude. H over L, we call that long waves. H, long length. That's a way of saying shallow water. And then gamma is the transverse flow variation. You put that into the equations, you now have parameters, you expand. First order, you take Koch and expand it one order. Sinh, expand it one order. Nothing else. Take the inverse Fourier transform. And this is what you get. This equation. This is the Benny-Luke equation. It just pops out immediately. Delta is Laplacian with a gap. So deform Laplacian. Gradient Q, deform gradient. If you take, we call this maximal balance. Epsilon is mu squared is gamma squared. Take that limit, go into a moving coordinate, you get an equation that at least I and UG and Sharby like. Whether anybody else likes it, I don't know, but this is the Kadamsev-Kashveli equation. One step below Benny-Luke. Benny and Luke didn't understand there was a maximal balance subcase below this. Work. Sigma twiddle is sigma minus a third. These are all normalized. So 1/3 is a special number. Okay? Sigma positive means strong surface tension, sigma less than 0, then you get weak surface tension, you get KP 1 or 2, depending on the sign. And UG and Sharby working on KP2, which is 0 surface tension. Think of that. That's more or less real water waves, if you will. But KP1 still has strong surface tension. You can get some interesting effects.